Hello and welcome. So that was a lot of information here. So let's try and summarize it all in one little table here. So let's start with zero order reactions here. So in a zero order reaction, what we have is a rate law where we've got the power of the reactant raised to the zero power. The units of K are molar seconds to the -1. And if you're wondering where that comes from, well, your rate is always going to be rate of change of concentration over time. So anything raised to the zero power is essentially just the number 1 with no units at all. And so the units of K there have to be exactly the same as the units of rate. The integrated rate law, we went ahead and looked here. So it looks just like the equation for a straight line. If you plot that on the y-axis and you put that on the x-axis, then your slope is minus K and your y-intercept is a0. So on the graph over here, this is exactly what we have. And the half-life we saw is essentially something that depends on the concentration of A. And you can see that as the reaction proceeds, essentially it takes less and less time for half of it to go away, and eventually it completely disappears at all. If you plot concentration versus time and you get a straight line, that's actually a test for a zero-order reaction. Now, if we go ahead and we uncover a first-order reaction, of course, what's first order about it is the fact that the power in the rate law, right, is raised to the 1. The units are seconds to the -1 for the rate constant. So why is that the case? Well, the rate has units of molarity per second. If you take a concentration to the first power, it's going to have units of molarity. And so we can see the only way for these to match up is if K has units of 1/seconds, because then 1/seconds times molarity is what you need. So that's why that is. In fact, you should be able to tell based on the units whether you've got a zero, first, or second order reaction. So the integrated rate law looks like this, or through properties of logarithms, we can show it can also look like this. Then if we look at the equation for a straight line, y equals mx plus b, we can see that this is essentially lined up for that kind of use. If you plot the logarithm of the concentration on the y-axis and the time on the x-axis, then you see a slope of minus K, sorry, I think I butchered that, and a y-intercept of the log of the original concentration. So if you plot this kind of graph of log concentration versus time, only if it's first order do you see that straight line with slope minus K. We also calculated the half-life. The half-life is essentially a constant, so you can see it takes the exact same amount of time for half the material to decay away. Actually, I guess you can't see because we're not plotting the concentration time curve, but we did earlier. And if we go to the second order reaction, so if I just uncover the very bottom, this table here is in your textbook, by the way, we can see the same thing as before. So rate has units of molarity per second. Okay, rate of change of concentration with time. And let's see, if you square concentration, it's going to have units of molarity squared. So your rate constant has to ensure the units on both sides are identical. So we need to get rid of a molarity, and we need to come with a second on the bottom. So that's molar to the -1, seconds to the -1, right? That's another way to write that. And then the integrated rate equation we saw looks just like the equation for a straight line, y equals mx plus b. So if you plot 1 over the concentration versus time, then if it is second order, so this is a test for second order kinetics, it will be a straight line with slope K. So there's the K right there, right? So that is our slope. And it's got a y-intercept of 1 over the original concentration. So almost always we're making these plots to tell the rate constant or tell if it's first or second or zero order, but occasionally we might want to know the original concentration, so the y-intercept gives us that. And we saw in the last video, right, that the half-life is changing, and so it depends on the original concentration inverted. So as the reaction goes along, right, as the original concentration goes down and down and down, every half-life, right, there's less and less of it around to get rid of. It takes longer and longer. And I always think it's kind of like eating ice cream because, you know, it's really easy to get the first scoop or two out of a bowl. And by the time most of your ice cream is gone, right, you're kind of scraping the spoon around and trying harder and harder and harder to get every last little bit. And it just takes longer and longer to get every last drop of ice cream out of the bowl. So that's second order kinetics for you. All right, let's move on to something a little different.